I'd like to thank the organizers and the conveners for the invitation. So I'm going to talk about ongoing work that we're doing on a global analysis of transverse spin observables. And this doesn't work. Yeah, so I'll first just briefly go through the kind of functions that we're trying to get after in this analysis. So talking about both TMD and collinear twist-free functions. I'll review kind of what we know about certain TMD and collinear observables like the Sivers and Collins effect and A sub n and PP collisions. And then talk about how we're going after a global analysis of all these different observables, and then I'll end with the summary and outlook. All right, so obviously I don't need to talk about and review TMDs to this crowd here. So we know we have 8 TMDs at leading twists for the PDFs and the fragmentation functions, and these have been well studied and talked about and discussed, so I won't say any more about those. And of course, if we integrate over these TMDs, we end up with the collinear functions, but this is actually non-trivial within CSS, as I think Leonard will talk about tomorrow. So what I want to just spend a few minutes on is talking about probably some of the functions that are less familiar to everyone, which are these collinear twist-free functions. So we have 3 different types of collinear twist-free functions, which we call intrinsic, kinematical, and dynamical. So the intrinsic functions, these are quark-quark correlators where we don't keep any KT on the quark line. We use a twist-free Dirac projection in the matrix element. So for example, this famous twist-free function GT is what we would call an intrinsic twist-free function. The kinematical functions are also quark-quark correlators where we keep the KT on the quark line. And after this collinear expansion about that KT, not surprisingly, we end up with first moments of TMD functions. For example, the first moment of the Sivers function showing up here. And of course, these are quark-quark correlators, so they're only functions of a single momentum fraction x. But then when we go to the dynamical functions, which are quark-gluon quark correlators, because the gluon is involved, we now have a dependence on 2 momentum fractions, x and x1. And again, these dynamical functions are quark-gluon quark correlators. And at certain kinematical points, for example, the soft gluon pole when x equals x1, there are some connections between these dynamical functions and the kinematical ones. For example, this function FFT at the kinematical point x1 equals x. That's what we call the Chu-Sturman function more commonly. Is the notation TF is used, but that's related to the first moment of the Sivers function. And then on the fragmentation sector, we have a similar set of functions. Okay, so we have our intrinsic and kinematical functions. For example, here we see the first moment of the Collins function showing up. And then the dynamical functions, again, are functions of 2 momentum fractions, z and z1. Because we don't have the time reversal constraint in the fragmentation sector, these functions are actually complex. So they have both real and imaginary parts, which is what these superscripts are indicating. Okay, so we'll see these functions showing up as well. Yep.
Sorry, what's the relation between the GFT and the GT tilde, the one we call GT tilde, so the difference between is it?
It's related. I would have to look at exactly what you have. It's probably related through some integral, I think, right? So you have this GT tilde of x, I think, yeah. So I think it involves some integral, maybe either just GFT or some combination of FFT and GFT. Yeah. Okay, so Elke had shown this data this morning for star for the Sivers effect in Zhou-Yang. Okay, so this of course is going after this sign change of the Sivers function, and we're looking forward to the more data and more precise measurements of this observable. We also have the pion induced Zhou-Yang from COMPASS. Okay, both of these giving an indication on this sign change in the Sivers function. Okay, and we've seen this data now as well for the Sivers effect in CITES from Hermes, COMPASS, JLab. where we get at this convolution of the Sivers function and the unpolarized function D1. So of course what has been done is to analyze this data and extract the Sivers function from this data. Okay, so these are more recent extractions. I apologize, I don't have the updated Torino extraction, but these are extractions of the Sivers function from this data. And what I want to emphasize is this extraction by Miguel and Zongbo and collaborators was done within the Collins-Soper-Sterman evolution formalism, okay, which we'll come back to later on why that's important. And then we have the Collins effect in incidus and E plus E minus. We've seen data on this and talked about this as well, that if we look at both of these observables, we can do a simultaneous fit then of the transversity function and the Collins function. And this has been done again by several groups. And here are some more recent results for transversity and the Collins function. And again, this work by Zongbo and Alexei and collaborators was done within the CSS formalism. We've also talked about hadron in a jet quite a bit, the Collins effect. And I believe there'll be a talk as well on getting at transversity through the dihadron fragmentation. So all of these have been studied and looked at as ways of getting at these TMD functions. Of course, the dihadron fragmentation is within the collinear framework. Okay, so what about the collinear observables that we want to study and understand? So the first one I'm going to talk about is a favorite of mine because it's a relatively clean observable and we actually can learn a lot from this. And Elke will tell me if SAR is close to having their data available for ACE-event and direct photon production soon. Okay, so we're still waiting on that, but there's a few papers out, and we have one giving predictions for this within the collinear twist 3 formalism. So we get this negative asymmetry where even though there's several terms in the twist 3 formalism that show up for A sub n in direct photon production, it turns out that the Chu-Sterman term, this term here involving FFT of x comma x, this Chu-Sterman function, which is connected to the first moment of the Sivers function, turns out to be the dominant piece of this. So this is actually kind of an indirect test of the process dependence of the Sivers function. Okay, and we can also then get at a clean extraction of this Chu-Sterman function. And something else that's useful, and of course, in terms of an EIC, I don't know if it's possible to measure this direct photon A sub n and EIC, but that would be the analogous observable at EIC. There's actually also work done in the GPM on this, but they actually find that the asymmetry is positive, where in the twist 3 formalism we find that it's negative. So this is actually a good observable to try to discriminate between these two different formalisms. Now, of course, the main observable in A sub n that's been studied now for over 40 years is A sub n in proton-proton collision. So the first data on this goes back to 1976 at Argonne, and then the most recent data here at RIC. This is from the Brahms collaboration, but of course we have even more recent data from STAR on pi zeros, and then Phoenix on pi zeros, and also now more recently on unidentified charge hadrons. Okay. And what was thought for many years was that, again, this Chu-Sterman mechanism was the main cause of A sub n. So the Sivers type effect, that was what was thought to have caused A sub n. Okay, there's work done by John Way and Werner and Zongbo on this, looking at this Chu-Sterman function as this cause of A sub n. But I don't want to go off on a tangent here, so I'll just get to the bottom line that basically now we do not believe that the Chu-Sterman function is the main cause of A sub n. Okay, there's several papers here. A lot of the authors are here as well about why we don't believe anymore that this Chu-Sterman term is the cause of A sub n. What we instead believe now is that it's actually a fragmentation mechanism, okay, of these partons fragmenting into these pions in the final state. And so what does that mechanism involve? So this was a calculation that Andreas and I did almost 6 years ago now, giving the first complete result for this term. So it's basically a coupling between the transversity function and then these three collinear twist-3 fragmentation functions. So we have the first moment of the Collins function showing up, this H function, and then an integral of this dynamical fragmentation function. It's the imaginary part of that function. And what we knew at the time was that these three collinear twist-3 fragmentation functions are related to each other. They're not independent functions. They're connected through this QCD equation of motion relation. Okay, so we have this relation between these three functions, and for purposes that we'll see later on, this integral here of h hat fu that shows up in this equation of motion relation, I'm going to identify as h tilde. So what we would like to have done is to eliminate the term in our analytical result involving this dynamical function, because we didn't know anything about that function. Unfortunately, at the time, all we knew is this equation of motion relation, and we see here that the integral showing up in the equation of motion relation is not the same as the integral showing up in our analytical expression for the spin-dependent cross-section. So instead, what we did was to eliminate the function h in favor of the first moment of the Collins function, which of course we had information on, and then we needed to parameterize and fit this dynamical fragmentation function. So this is what we did back in 2014, and we also included the Chu-Sterman term, but we fixed that through the first moment of the Sivers function. And what we found is that it's actually the fragmentation term, okay, that's giving this rise in a sub n at large xf. Okay, so these are just the different pieces of the term, but we see that it's actually the fragmentation mechanism that gives this rise in a sub n at large xf. And this black dash curve is the result from the Chu-Sterman term. So it's actually quite small, and if it is sizable, it's actually opposite in sign. Okay, so our conclusion in 2014 was that this fragmentation term can be the main cause of a sub n, and the Chu-Sterman term is actually quite small. So since that time, we actually derived, yes?
So once again, so for the Chu-Sterman part, you are taking the Sivers fields from the maybe the old Torino field.
Yep.
Okay. Then for the fragmentation part, yep, you are fitting the H, or you are
yeah. I didn't write it out here, but we basically cooked up a parameterization for this H and fit those parameters to the RIC data. Okay. Yeah. And the transversity and the Collins were fixed also from Torino fits.
Right, but the biggest contribution seems to be the one from the H.
Yeah. So I mean,
the part in other words, the part coming from the Collins function alone is sizable or is small?
Well, let me get to later on in the talk where we update this analysis, and we'll see that it's. So okay, this was 2014, so this was a fit of this function. We've updated this, so I don't want to dwell on something that's 4 years old now. But yeah, we fit this function to the RIC data, and found, I mean, the bottom line that I wanted to get out of this was back then we made the claim that the fragmentation mechanism, forget about what is coming from which term, the fragmentation mechanism can describe a sub n. Okay. We don't need the Chu-Sterman term.
Okay, but only by construction, because you put some function in and you scale it so that it has data.
Okay, so let me fast forward like 3 years to when we update the analysis, and then you can see what's going on and that this claim is still valid. Okay. So we derived an additional relation between these three functions a couple years ago. It's running under the name of a Lorentz invariance relation. This is a paper with Mark and others. And so we see now what's nice about this relation is that the integral showing up here is exactly the same integral showing up in our analytical result. So what we are able to do is actually eliminate this term from our analytical result in favor of H and the first moment of the Collins function, and then further to eliminate H in favor of the first moment of the Collins function in H tilde. So now, our analytical result, okay, of course the hard factors are different once we insert these functions, but it's a coupling now of the transversity function to the first moment of the Collins function and this H tilde. Okay, so this is the work about 1.5 years ago with Leonard and Alexei and Zongbo. Okay, so what we wanted to do was to say, we're not going to do any fitting. We're going to take known results for the transversity function and the Collins function. Okay, because in principle now that we have an additional constraint on these functions, our result from 2014 might be spoiled. Okay, as Gunnar pointed out, we were fitting a function, so that we didn't know. So maybe that gave some bias and gave this large effect. So what we decided to do is to say we do no fitting. We take the transversity function and the Collins function that's been extracted from sidis and E plus E minus. For the time being, we ignore this H tilde function and we just see what we get. Okay? And what we found is that we still get a sizable result for A sub n from this fragmentation term. So again, this is no fit. Okay, that's why it's off from the points. But the idea is that if you take transversity and Collins from sidis and E plus E minus and use it in A sub n, you still get a sizable result for the fragmentation term, having done no fit. Now that you look at this and maybe it's not so clear, there's a large uncertainty band here. Where's that large uncertainty coming from? Well, it's the fact that the transversity is not constrained at large x. Okay, we all know this. Sidis data does not constrain transversity at large x. So to turn that around, we can use A sub n data from proton-proton collisions to actually constrain transversity at large x. Okay. Yes? We're going to get to that. Let me this is the point of the talk. Okay? I can make the talk 5 minutes and get to the bottom line, but I want to give you some background on where we're going.
So in this calculation, basically, when H tilde equals 0, you could call it a Van-Zurabie-Check approximation.
Yeah, but I don't want to call it a Van-Zurabie-Check approximation because this, as we'll see, this function H tilde cannot be 0. If it's 0, the Collins function is 0. Yes.
One question. When you say it's not constrained, you mean we have huge error band, but it's not really true for the and then you have this upper bound. So what does that error come from?
This comes from, so when in the Torino, or actually it wasn't the Torino fits, it was the fit by Alexei and Zongbo, they have errors in their parameters. So it's kind of looking at the range that you get for A sub n by varying the parameters of their fit within their range. So, yeah.
I think the error is pretty small at large x. So the way we propagate it is huge. Because it becomes every small error becomes really huge.
Well, I mean the 1 minus x to the beta, that beta is has a large uncertainty to it. And in A sub n, we're integrating from some x min up to 1 on the x in the transversity in h1 of x. So that's why it becomes so large then here, because we basically have to extend it all the way up to 1.
The error on transversity seems to be small because the transversity is dying and x goes to 1. But the relative uncertainty is still very huge. Okay, so here you need to integrate. So of course you don't know what is the x for the transversity.
So you integrate from where to where?
Some x min to 1.
X min to 1.
Oh, okay, so then that's all range.
Yeah.
That's why you pick up all the uncertainty in relatively large.
Okay, so it's not just the large x.
No.
It's basically the whole.
Yeah, you pick up the whole. Okay, so before moving on, I wanted to also talk about A sub n and the PA collisions, where STAR has data on the pi 0, A sub n and PA collisions, and they find no suppression with A. Phoenix has results for A sub n for unidentified charged hadrons, and they find this a to the 1/3 suppression with a sub n, and I was told that there is no tension because it's different kinematic regions, but I'm actually puzzled by that because I think there is a tension in the results between star and Phoenix or what they get for a sub n. So maybe that's left for later discussion. So what was done by Yoshi and his collaborator was to look at our fragmentation mechanism and see what happens when they include multiple rescattering corrections to this. What is the behavior of these terms? Is the results from, okay, at that time there was only the star results, the Phoenix results weren't out yet. But what happens to this fragmentation mechanism? Is it consistent with what they are finding in PA collisions? And so what they found was that, and this is going back to our 2013 expression, that this term here has the a to the 1/3 suppression along with this H term. This term here is not suppressed with A. So what we wanted to do was, now that we had this Lorentz invariance relation, we actually have a better constraint on what this term is. We wanted to rewrite it, okay, using this Lorentz invariance relation, and again, do no fit, and simply look at what happens if we just look at the terms involving the Collins function, again, not doing any fit. What size do we get for this term? Okay, that's basically going to determine whether the observable is suppressed by a to the 1/3. So if this is small and these dominate, then it's going to be suppressed by a to the 1/3. But if this is dominant, then it's going to have no suppression with A. And right now it's kind of inconclusive again because we have these large uncertainties. So it could be that this term is sizable, but we need to reduce these uncertainties. Again, this goes back to actually including a sub n data along with the CITUS and E plus E minus data in a fit of transversely. Yeah. Yeah.
So the average PT is 2.9 GeV, right?
Yeah.
It's very difficult to explain this using the saturation microscope because PT is too high.
Yeah, I mean, yeah.
Scale is much smaller.
Right.
So very possible.
Yeah, this is.
This data is a kind of axis in the muon arms. So it's between 1.1 to 2.1 or 2.2.
Yeah, 1.4 to 2.4.
Yeah, exactly.
Yeah.
So it is not really in a saturation regime. As a saturation scale should be, I don't know, 0.5 or something like that compared to. So I'm indeed that one doesn't work. And why do you think that actually there is inconsistency between these two data sets?
Well, I mean, even down to a PT of 2 here, it's flat, and I think even for XF down to 0.2, which is where this is going, it's flat. So I mean, I don't know. I trust the experimentalists if they tell me that there's no tension between the data.
The underlying subprocess change versus rapidity? Because as the harvest data, I guess, the star data is of course between 2.8 to 4. So it is a significantly different rapidity. Yeah,
okay, so I mean, I don't want to get hung up on the PA stuff, but yeah, and then we have to think about it more. I mean,
the star rapidity is 2.8 to 4.2, so it's the FMS. So
I mean,
it's a very different rapidity range.
But still, probably most people do want scattering.
Yeah.
I think X is very small.
Yeah, X is between, well, the XF is between 0.1 and 2. Okay, maybe we can discuss this more. Okay. And because we wanted to talk a bit about the EIC, I wanted to also show A sub n and EP collisions. So this was work that we had for a leading order calculation of this result compared to the Hermes data. So we're clearly above the data here. But again, this was back in 2014. We need to update this to include the constraints from the Lorentz invariance relations. But again, this will be crucial at the EIC to measure this observable as the analog to the PP A sub n. And here we actually think that next to leading order corrections would be significant, and I think Werner might be talking about this tomorrow a bit, so I'll leave that to him. But again, this EP A sub n is going to be extremely important at an EIC as the analog for the PP A sub n that's been measured at RIP. Okay, so basically I've talked about 4 different types of processes here. So we have semi-inclusive DIS with the Sivers and Collins effect. We have E plus E minus with the Collins effect. We have our Sivers effect in Drell-Yan, and then we have these A sub n measurements in PP collisions. And clearly, we all know that there's connections between these TMD observables that the TMD functions are showing up. For example, the Collins function shows up in Sidis and E plus E minus. The Sivers function is showing up here in Sidis and Drell-Yan. Okay, so there's obviously connections between these 3 TMD observables, and the functions for the A sub n observables are here that we discuss is the transversity function, FFT, the first moment of the Collins function, and this H tilde. So the question becomes, how do we actually connect the TMD observables to the collinear ones and get after some global analysis of all of these observables? Well, as I mentioned before, if we look at some of the recent phenomenology on the TMD observables working within this Collins-Soper-Sterman formalism, well, if you go into these papers and look at what they're doing, they're taking the TMD in B space and they're writing it out in this operator product expansion where the function that's actually showing up here is the collinear twist-3 function. Okay, so if you go into the paper by Miguel and Alexei and Zongbo, what they actually fit and parameterize is the Chu-Sterman function, along with the non-perturbative pseudocall factor that's dependent on the function. Okay. Likewise, if you go into the paper of Zongbo and Alexei and their collaborators, where they fit Sidis and E plus E minus Collins effect, they write out the B space version of the Collins function, and in the OPE, it gives you the first moment. Okay, so that's what they're actually parameterizing and fitting, the first moment of the Collins function, again, along with the non-perturbative pseudocall factor. So what that means is that the way we should be thinking about this is within the TMD observables, the functions that are sitting there that are underlying them are the same functions that are showing up in the A sub n observables, the collinear observables. Okay? These are the functions that are underlying these transverse spin effects. And now you look and you say, oh, this H tilde function is sitting here. What is that? It's some new function that shows up in the collinear twist-3 framework. Actually, that's not the case. Gunnar had this in his slide yesterday, that if I look at AUT sine phi s and Sidis, okay, the unintegrated version I think has something like 4 or 5 terms in it. But if you integrate over PT, you're actually left with 1 term, and it's exactly transversity times H tilde. Okay, and Compass has data, Hermes also has data on this observable, and it also shows up in the analog observable in E plus E minus. There's an additional term here that vanishes in Sidis because of time reversal and time reversal constraint, which it doesn't in E plus E minus. That's why we have 2 terms there. So we can actually stick H tilde in here in Sidis and E plus E minus, and now all of a sudden we have the same function showing up in all 4 of these different types of observables. Okay, and this is where we're getting at now towards a global analysis of all of these observables. Before I get to that, I want to mention that if we actually take the equation of motion relation and Lorentz invariance relation, and these have been derived now for all twist-3 PDFs and fragmentation functions. Okay, we have 2 equations and we have 3 unknowns. Well, we know from mathematics that means 2 of the functions are not independent. Okay, so we can actually solve for H as this integral of the dynamical fragmentation function. We can solve for the first moment of the Collins function as an integral of this dynamical fragmentation function. Okay, this is why I say that this Wanzer-Wilczek type approximation is actually theoretically inconsistent, because remember, H tilde is also an integral of this dynamical function. So if I set H tilde to 0, that means I'm setting this dynamical function to 0, and if I set the dynamical function to 0, I'm setting the Collins function to 0. So we know that's not true, so it's totally theoretically inconsistent to use a Wanzer or Wilczek type approximation in a T-odd observable. And so really, this table that I had at the start of the talk is kind of redundant in terms of these intrinsic and kinematical functions. Really, we can reduce it down to just the dynamical functions. And I would argue then that all transverse spin observables are actually driven by these dynamical functions, the multi-parton correlations. Okay, so really, what's sitting here underlying all of these observables are dynamical quark-gluon-quark interactions. That's what's driving these transverse spin observables. Now, of course, from a practical phenomenological standpoint, okay, because of how we see that there's complicated integrals showing up with these functions, it's more practical to actually try to fit the functions like transversity and the Chu-Sturman function, the first moment of the Collins function, H tilde, to do a global analysis of these observables where we're fitting all of those functions. And so this is what I'm going to show as very preliminary results where we've done a global fit of the Collins effect in E plus E minus, Collins effect in Sidis, integrated AUT sine phi S in Sidis, A sub n and proton-proton collisions, only the fragmentation term for now. We're also going to add in the Sivers and the Chu-Sturman function for A sub n, okay, into this global fit. We use Monte Carlo sampling to try to get the error bands. For now, we're just sticking with the simple Gaussian ansatz for the TMDs. Okay, so we have solutions for these non-perturbative functions, including H tilde. Okay, it's highly non-trivial given all these different observables. And then I think this was mentioned a few times about getting the flavor separation needing more precise data on the deuteron, and hopefully an EIC can help with that. So this is what we get for the Collins effect in E plus E minus. Okay. And okay, here we have the Collins effect in Sidis. For Hermes proton data, compass proton data, compass deuteron data. Okay, here's the AUT sine phi S asymmetry, okay, for unidentified charge hadrons. Here's the Rick A sub n for pi zeros here on the left, and then the charge pions here on the right. Okay. And then the functions that we get out from this. Okay, so here we have our transversity function. Okay, we have the Collins function, and we have H tilde. Again, this is very preliminary. Okay, we have to look into this more carefully with the Monte Carlo analysis. Okay, but this is what we're trying to get after, is this global analysis of including all of these observables, because they actually all have the same functions sitting there. Okay, so just to conclude, so the TMD and collinear functions are highly interconnected, especially for transverse spin observables. We need to treat both observables on the same footing. Okay, it's not TMD is different from collinear. Okay, it's all the same functions showing up. We're working on a global analysis of all of these observables. So again, the Sivers and Collins effect, A sub n and PP collisions, AUT sine phi S. And an EIC will be important to measure these, not only the Sivers and Collins effects, but also these A sub n observables, okay, like single inclusive pion production, that also have to be measured there as well. Thanks.
Question?
Does any of this include D-club evolution?
Of our fit, we haven't included any evolution yet.
So which scale is those transversity you were showing?
So that is at the, so I mean, all of these data are sitting around, yeah, so it's about a Q. I think I have to look back at what I put in, but I think it's 2 GeV.
2 GeV squared or 2 GeV?
No, Q of 2 GeV. I have to look back at what I put in.
So the average Q of the
Sorry?
So there's no evolution and you're including plus minus data as well?
Yeah, I mean, okay, eventually we're going to include evolution, but at this point it's, I mean, we're trying to, yeah, I mean, we're trying to fit. I mean, it's okay. I mean, the Q and the PT Rick is maybe not, the Q at plus or minus and the PT at Rick is maybe not so different. I mean, yeah, we have to look at that, but for now, we're starting with the simplest possible sort of analysis to see, can we just get reasonable solutions and then start adding the layers on top of that.
Excuse me, I'm a bit confused. I go back to my question because if you involve also case of N data. So again, I'm confused. What is the R scale which is in this business? Because there, if you change PT, PT by PT, you're changing the scale. So you don't have evolution. You certainly go far beyond the 2 GB limit that you were mentioning. So when you plot the transversity, I don't understand at which scale I should take that result.
Well, there's no scale because it's just
There's
one
no,
bit,
yeah.
which
With no evolution.
It's just one.
So it's like an average of the Qs of the
No,
experiment.
because that average, I mean, at least on the top, is 4 times larger than what we get analyzing out of our global feed. So,
Well, we're including more data though, so I mean, I think Nobuo will talk about this with unpolarized. Once you include more data, your functions can change. I mean, there's nothing that restricts your function to be what it was when you included only a subset of the data. So, I mean, there's nothing that says the transversity function has to be exactly what it was in citizenity plus E minus analysis. We're including more data. So,
some our global feed is also proton data. So it's
yeah, we have
similar
proton.
to yours as a kind of qualitative analysis. So, right.
But it was continued because you have the Gluons in there. I guess. Can you just tell us how you parameterize your function? How many parameters do you have, and how many data points?
I mean, the data points, it's like 370 something. I mean, it's whatever it is for citizen E plus E minus plus, I don't know, what is there, like 30 points from here and maybe another 60 from Rick. So it's, yeah, it's like 370 something data points. Yeah, so the number of free parameters, something like, yeah, something like maybe, yeah, I'm trying to think back at what parameters you said equal to what, but I mean, you had parameterization for transversity, Collins function, and now H tilde. So, well, Sivers isn't in this. Eventually we'll have Sivers, but Sivers isn't in this. There's no Sivers in this.
So I missed this one. So
Yeah, yes.
At the moment, you did not include.
Sivers we didn't include.
Because you are assuming that most of it comes from, most of the A9 comes from the fragmentation.
Right. Yep.
But in principle, you can include it.
Yeah. I mean, the only effect it has is it will kind of tweak a bit what's going on with A sub n, but the Sivers effect in CITIS is kind of its own analysis, right? So.
Yeah, but for the TBAP evolution, you did include the approximate way of including it.
Well, it's in the code. It wasn't included. Yeah.
But in principle,
yeah,
there are ways of mimicking TBAP evolution even without solving TBAP equations, because this penalizes, just processing too much. So this was. Order of 10 to 12 to 15.
Oh, sorry, Dennis. Yeah, so like 15, yeah, order of 15 parameters.
Just proof of principle that this looks solvable, at least in this sort of format.
So I just have a very naive conceptual question. So in the good case, in the ranking series, where they use the Lorentz function to explain, like, say, the 0 and it was always like half of the condition. just conceptually, where do we get to the same underlying functions? Was it a completely wrong approach? Like something must have been missing, or was it a different new approach? So I mean,
No,
It's the same approach.
right, but why? So I think the most it's just use the TMD approach. Some
But we're not doing the TMD approach. That's the whole point.
Exactly.
It's the collinear twist 3 functions that are I mean, it's the TMD approach for the TMD observables, right? So Sidis and E plus E minus, the functions that are showing up are these. It's the TMD approach. But the point is that these functions here are what show up in the collinear twist 3 approach. So we're using the collinear twist 3 approach where it should be used with A sub n, and we're using the TMD approach where it should be used with Sidis and E plus E minus.
you know, I understand that.
Yeah.
In some sense, you know, the
Are you specifically, especially allowing on an idea?
so I'm just wondering because in some sense you basis all of the things. Yeah, okay, I mean,
Why don't you fit that with a more fundamental function that you have found? Why don't you fit that with a more fundamental function, the numerical function that we have found?
Why don't we fit it? Because it shows up in these integrations, and it's well, it's a I mean, we could, but it's, I mean, let's start with the simplest. Yeah. I mean, this is a function.
Instead of
Yeah.
fitting the two-dimensional functions, you fit some projections of these functions. That could be used otherwise. So it's yeah, but it's already difficult to fit the projections. It's impossible to fit.
Also, the Collins function is.
Yeah, thinking ahead a little. So this is great, of course, but if you at some point want to get really serious and they include deep level evolution, right?
Mm-hmm.
Is it known for all ingredients completely? And also is it obvious that all the relations you're using are preserved under renormalization?
That's a good question. We're looking into that. We believe they should be. So the answer is, for the evolution, it's known. As you know, it's known for the two-Stirling function and also for this first moment of the column. Now, mixes, of course. I mean, it's not a closed evolution, so you would have to do something so you could deal with that. But yeah, the evolution here is known for these functions. So at some point, yes, I think we can implement the full evolution for them. I believe that the relationship hold, but I mean that's that's something we're looking into as well. If you go to next to leading order, do these relations hold? So yeah, but I believe it should be okay. I mean, if this is leading order in the OP, right? If you go to the next to leading order, you're going to start to get mixing with the off diagonal terms, right? So, okay, but in terms of the analyses that have been done, this is what has been done, and then you can connect it to the A sub n. If you go to next to leading order here, probably for consistency standpoint, you would have to go to the next to leading order to A sub n, and then that's probably a very heavy lift to do that. So.
If you take the GH parameters and GF parameters from elsewhere, you fit them too.
Okay, so what we do at this point is just a simple Gaussian ansatz. So we're fitting the width of the Gaussian, and we're fitting the parameters in the collinear part. So we're not going full out CSS like they did in this analysis. Okay, so eventually that's what we need to get to, but we're just going to start kind of how it all started with just a simple Gaussian ansatz, fitting the widths and fitting the collinear the collinear part as well.
I mean, I guess to go beyond that, Gaussian at the moment would be sort of premature in the sense that you don't have high order corrections and resolution for the other pieces either.
Yeah.
So I think it's a good start.
Any other questions?
You start for your function, whatever you start from, you take the fix from the TND case, right? And you take the value of the width of the Gaussian. Did you in your calculation, did you take into account the error of that parameter as well? Because your function in the collinear T3 approximation are the moment of the TND function that we extract. So to compute these moments, you have to integrate over the KT.
Yeah.
And there is an error on the parameterization that we can extract for this KT, and this can probably enlarge very much the error band that you showed, for example, in the Collins.
Yeah. So the parameterization is done so that when we write down Sivers function or the function of x and kt, the collinear part that's sitting there is exactly the Chu-Sterman function. Okay, so when we do the integration, we just get the collinear piece. So the width isn't showing up in the collinear piece. It's only showing.
The integration, the error that you have on the width will reflect on an uncertainty on the function that you get.
Analytically, the width is not showing up in the collinear function, right? We parameterize it such that the collinear piece is the Chu-Sterman function. And then the exponent, the Gaussian that's sitting there, it's normalized so that it just,
And by construction, always gives you back.
it's in the paper that Alexei has with in looking at fitting transversity to the lattice data in Citus, right? That's what they do now, right?
Yes, so this error
Doesn't propagate into the collinear function anymore.
It depends on the parameterization. If you chose a different one, where after integration the link is there, of course you have to propagate.
Gunnar?
Comment on the question. So I think you're fitting now the sine phi as assuming it's already tilde, which is probably it has the other terms still in there, but the test at some point. But
That's the
Well,
it's integrated. It's already in the X projection, but
yeah, okay, yeah, it's as good as we can.
But the other thing you mentioned that each tilde has to be non-zero because transversity is non-zero. Collinear function. But there are moments or there are integrals of two different integrals of this dynamic function. Is it really excluded that one of them vanishes? Is it really
if you want to find a function whose integral for h tilde vanishes, oops. I guess it is possible, right? So I don't know. I find it hard to believe that you're going to find a function here such that you integrate it and you get 0 for this integral, but then you do this integral and get non-zero. It's possible. I don't know. It is possible because you're right. They are integrals, but to me, it seems like the most natural way for h tilde to be 0 would be if this function was just 0.
Before I repeat the statement somewhere else, I want to make sure that so it's actually.
I think sorry. I think that, however, the reason to put h tilde to 0 is a Gonzalo-Wilczek type of reasoning, right? And then the Gonzalo-Wilczek type of reasoning would say all quark effects are 0.
Such as
So in this sense,
Such as
in
Sivers.
this sense, if you take this approach, then you should put everything to zero. In this sense, the function, the original function itself should be zero.
Yeah. No,